So we, in the undergraduate graph theory course, we also learned several variations of the graph coloring. One of them is this list coloring. So when a list assignment is given, so for each vertex you have a graph, then there are certain list of colors that you can use on each vertex. So on this vertex you can either use 1 or 2, or one on here you can either use 1 or 3. Here you can use 2 or 3. And then can we choose one of those colors so that the resulting coloring is proper? That's the list coloring. So arrow V indicates it's this set, and you have to choose the color from this acceptable, set of acceptable colors. And then we say that a graph is K-choosable or K-list colorable if whenever all the available colors at each vertex is at least, there are at least K colors available, then we can find the proper coloring F from, we can select one color from them, from each set, so that the resulting coloring is proper. And least chromatic number or choosability is, we write in this way, chi sub L, and which is the minimum K such that this is K choosable. And in the, we learned that with this concept of list coloring, greedy coloring also works as it is, as before. So we can actually prove this upper bound of delta plus 1. Also, the list extension of the Brooks theorem works, so that if G is a connected graph, if G is connected and this is not a complete graph or O cycle, then the list chromatic number is at most its maximum degree. Another variation of the graph coloring is instead of coloring the vertices, we can color the edges. So we give the color 1 here and 2 here, say 3 here, so that the two edges which shares the same vertex gets the different color. So which is edge coloring. And we say that the graph is K-edge colorable if we can properly color the edges with K colors. And we denote the edge chromatic number or chromatic index as this chi prime of G is the minimum K such that G is K-edge colorable. And it's easy to actually see that this edge chromatic number or chromatic index is same as the chromatic number of the line graph of G. So here line graph is a graph, for each, this is G, then this is E1, E2, E3. For each edge we put a vertex here, and then we add an edge between them if these edges share a vertex in G. So this new graph is called the line graph of G. And if we just use the greedy coloring, then we can easily see that its edge chromatic number is at most the maximum degree of line graph plus 1, which could be as large as 2 times maximum degree of G minus 1. So we can easily show this, but in here we ignore the structural information of this line graph. So this is not any graph, this is line graph of some other graph, so it gives us some structures. For example, one of the structures it has is that whenever a vertex has 3 neighbors, there must be an edge between 2 of them. So this cannot be the independent set. So in other words, this is claw-free. Claw is if induced subgraph in G, if we can pick 4 vertices, which has one vertex has 3 neighbor, and then this forms an independent set, and this is called claw. Claw-free graph means that it doesn't contain this K13 as an induced subgraph, and this is claw-free. So this line graph is claw-free because if if we have 4 vertices and then one is adjacent to 3, that means in the original graph we have this one edge E and then 3 other edges. And if you have 3 other edges which shares the vertex with E1, then at least 2 of them must share the same vertex, say B or U. If 2 of them share that, then they are also adjacent. Anyway, so we can, because there is some structural, information on the line graph, we can actually improve this bound to get this Beijing theorem. We know that for graphs, its H chromatic number is either maximum degree or maximum degree plus 1. This lower bound is easy to see because if there are delta of G many edges sharing one vertex, then they all must have different colors. And then Beijing actually show that for multigraph, let's write this mu of G with the maximum edge multiplicity. So UVW, let's say this VW has there are 3 edges between this VW, then let's say this is the edge multiplicity 3. And for graph, we take the maximum edge, multiplicity of the pair, then let's write that as mu of G. So we know this. And for simple graphs, so graphs are simple graphs in our language, so it's either the H chromatic number is delta or delta plus 1. So in this case, we say that the graph is class 1, and in this case, we say that the graph is class 2. So all of these were what we learned in undergraduate graph theory. And let's consider let's combine these two concepts of list coloring and edge coloring. So we can consider list edge coloring. So for, all you can, call, it can be called edge choosability. So for each edge E, we have a list E. And then we want to choose color that we want to use for this edge E. Then we can consider this list edge chromatic number of G, which is same as list chromatic number of line graph of G. So because the grid coloring again works for list coloring, so this is at most maximum degree of this list chromatic number, list graph, maximum degree of line graph of G plus 1, which is at most 2 times delta of G minus 1. So this upper bound holds. But can we do even better? Actually, there is conjecture says that which is list coloring conjecture, which is list color conjecture, or give me a moment, which says that for every graph, the list edge chromatic number is same as edge chromatic number. So it is not known whether this is true, but if this holds, then we have that this list edge chromatic number is at most the maximum degree plus 1. Because this together with this Beijing theorem implies this. But we don't know whether this is true. I mean, as some partial result, can't prove that this is actually 1 plus little of 1 times delta of G. Meaning that for any positive epsilon, I mean, if G is large enough, then, I mean, if delta of G is large enough, we have this upper bound. And later, Morley and Reed improved this to the following better bound. So delta plus delta to the 1 minus 1 over k. So here let me check what's k. Sorry, let's write this as a half. They actually prove it for any linear hypergraph, k uniform linear hypergraph. So that k comes from the uniformity, but let's just say in this case, which we just consider the case of graph. And what we will prove is this theorem by Garvin. He proved this least coloring conjecture for bipartite graph. If G is a bipartite graph, then we have this least edge chromatic number is actually same as the maximum degree. And we already know that the maximum degree of, for bipartite graph, the edge chromatic number is same as maximum degree of G. So this is what we will prove next time. But before that, let's define something which is useful for, the proof. Let's say a kernel of a digraph. Let's define what it means to be a set to be kernel of a digraph, which is a stable set S. Stable set is same as independent set, so set which doesn't contain any edges inside, having an out neighbor of every vertex outside S, meaning that we have here, and then every vertex outside has at least one out neighbor in S. So if there is some vertex which doesn't have any out neighbor of S, then S is not a kernel. And we say a digraph is kernel perfect if every induced subdigraph has a kernel. And let's define one more concept. Given a function f, which assigns a natural number on each vertex of G, we say the graph G is f choosable if a proper coloring can be chosen from the list at the vertices whenever the list size at x is as large as fx for each x. In other words, if we let f be the function from G to, say, natural number such that all the vertex its value is k, then f choosable is being same as its least chromatic number is at most k. So this f choosability is more general. So this this least chromatic number being at most k requires that if every vertex has a list of size at least k, then we can finish the coloring. But here, this f choosability gives a restriction which depends on the vertices. So some vertex it might have a larger list, some vertex it might have a smaller list. So it's more flexible definition. So we define this f choosability and we define this kernel and what it means to be a digraph to be kernel perfect. So using this concept, next time we will prove this Kelvin theorem. That it's least h chromatic number is same with the maximum degree for bipartite graph. That's what we will do next time.